Welcome to NH Tech. Today, we're going to design a Gilbert Cell Mixer using Keysight Advanced Design System. Before we begin, let's quickly review the basic concept. Here you can see the block diagram showing how the mixer operates. An RF mixer is a 3-port device that takes in 2 signals, the radio frequency signal and the local oscillator, and multiplies them together. This process generates 2 new frequencies, the sum and the difference of the inputs, giving us the desired intermediate frequency. And this is the Gilbert Cell Mixer circuit, one of the most widely used active mixer topologies in RF systems. It consists of 6 bipolar junction transistors, arranged to provide balanced mixing, good conversion gain, and isolation between ports. Now, let's start building this step by step in ADS. First of all, create a new schematic. From the component palette on the left, insert a BJT transistor. Double-click on the transistor to open its component options. Under Parameter Visibility, click Clear All to hide unnecessary parameters. Next, place 3 transistors vertically. And then flip 3 more horizontally to form the symmetrical mixer structure. Now, connect the transistors as shown in the Gilbert Cell circuit diagram. After that, place 2 resistors and connect them to the collector sides of the upper transistor pairs. Complete all connections according to the circuit diagram. Place a current source. Connect it to ground. Now, insert the pins. Insert the pins for DC supply, intermediate frequency, radio frequency port and local oscillator port. Assign pin names as follows: VDD for the DC supply, IF plus and IF for the output ports, Low plus and LO for the local oscillator inputs, and RF plus and RF for the RF signal inputs. Now, change the resistor values from 50 ohms to 300 ohms. Next, insert a BJT model into the schematic. This step is essential to perform accurate simulations. Different parameters of the BJT model are provided, and you can adjust these values according to the specific transistor or device you're using. Now change the current from 1 mA to 15 mA. Save the schematic. Next we are going to create a symbol for the mixer. For this, go to Main menu, and click on Create Symbol. Press OK to proceed. This is the created symbol. You can modify and arrange the symbol layout as you like for a clean and professional look. Now, create a new schematic and insert the mixer symbol you just made. We'll now set up the input and output networks for simulation. Search for the balun transformer in the component library, and select a 1-to-1 transformer. Connect one transformer to the RF plus and RF terminals, and use the single-ended side for the RF input signal. Place two other balun transformer, one for local oscillator and second for IF output. Make the connections. Now place a DC power supply. Use Ctrl+R command to rotate. Connect one end of this DC power supply to ground and other end is connected to VDD. Next, go to Sources, Frequency Domain, and place a tone source for the RF input. Use Copy-Paste command to place another tone source for the local oscillator signal. Make the connections. To adjust the position of text, first select the item and then press F5. Assign a port for intermediate frequency. Now search for Harmonic Balance Simulator, and place Harmonic Balance Simulator into the schematic. Now set RF input level as -10 dBm. And the value of radio frequency is 1 GHz, and set the local oscillator input level as -3 dBm. And local frequency as 90 MHz. Now, double-click on the Harmonic Balance Simulator to configure the simulation settings. You'll notice that the 1 GHz RF frequency is already listed. Add another frequency entry for 90 MHz. That's for the low signal. Set the harmonic order to 5 for each tone. If you're interested in analyzing more harmonic components, you can increase this number for higher accuracy in the output spectrum. Now, run the simulation and select a rectangular plot to display the results. Plot the if output in dBm. Here you can see the results from the harmonic balance simulation. As we discussed earlier, two output frequencies are produced. One at 1 GHz plus 90 MHz equals 1.09 GHz, and the other at 1 GHz minus 90 MHz equals 910 MHz. Place a marker on the output peak to measure its level. You can see the output is around +20 dBm. Now, let's change the RF input power level to -20 dBm and run the simulation again. Notice that the output power has dropped to approximately 17.5 dBm. This indicates saturation, meaning the output response is no longer linear. To analyze this behavior more efficiently, initialize a variable for the input power level. You can also experiment by changing the RF frequency. For example, increase it from 1 GHz to 2 GHz. Run the simulation again, remove the previous marker, and place a new one on the output peak to observe the change. Finally, to view the complete response, double-click on the Harmonic Balance Simulator and open the Sweep Settings tab to configure frequency or power sweeps.